Thank you all again for joining us for today's CE Appetizer. And I would like to introduce today's speaker to you, Nikola Markoski. Nico obtained his PharmD from Purdue University's College of Pharmacy and his MBA from Krannert School of Management. He also completed a non-traditional PGY1 and PGY2 HISPAL at Northwestern Memorial Hospital. Nico is currently manager of pharmacy analytics and clinical insights at Vizient Incorporated. In addition to his day-to-day responsibilities, Nico is responsible for strategic programs in pharmacy sourcing at Vizient. In his role, he serves as a subject matter expert on drug shortages and analytic capabilities, and is also lead of the End Drug Shortages Alliance Rapid Response Team, where he is tasked with all the data analysis surrounding drug shortages. Nico is the current director of ICHP's Division of Marketing Affairs and the 2023 recipient of the ICHP New Practitioner Leadership Award. Dr. Markoski, thank you for joining us today.
Thank you again. For those of you just joining, my name is Nikola Markoski, and today we'll be talking about AI and doing a review really of sort of the back-end understanding of the technology itself, specifically how it relates to pharmacy, some use cases that are already being used or being considered within the holistic pharmacy domain, and then considerations as this will most likely impact everyone's practice at some point. So for disclosures, I or the course director, presenter, and reviewers have no financial relationships to disclose, and this activity is being presented without bias and without commercial support. As a disclaimer, CE credit for this presentation will be available at the end to both pharmacists and pharmacy technicians. So some of the objectives we'll be looking to cover today, we'll actually be analyzing an artificial intelligence framework, diving deeper than probably what most of you have seen. We'll be evaluating the relationship of data inputs and metrics as it influences artificial intelligence outputs. So basically understanding what you have to put into AI in order to get the output that you receive. Looking at artificial intelligence examples and applications within pharmacy practice, again, across the entire pharmacy domain. So industry, institutional, retail, etc. And then also looking at the current and proposed policies and legislation surrounding the utilization of artificial intelligence within pharmacy, as it's still a little bit hazy. So starting off with, we'll look over some definitions, framework, and design. So the first thing to know when you're talking about AI, most individuals, when they think of AI, they think of some sort of futuristic sci-fi state where you have some large, intelligent, either metacomputer or robot basically answering any and all sort of problems that humanity has. The reality is AI is much deeper than that, to be quite honest. While yes, there is an aspect, a type of AI that kind of does correlate to that sort of self-awareness, or the example most people think of when they think of the sci-fi examples. The reality is AI can also be as simple as some automation that we're already seeing in day-to-day. We just don't necessarily think of it in AI terms. So before we dive deeper into any sort of framework, it's important to understand, how do you actually classify AI? When you're reading, articles or looking at potentially a sampling of AI, it's important to understand what sort of stage it's in and what sort of type. So starting with the staging, it's very simple. It's ANI, AGI, or ASI, or the three main classifications or stages of AI. So starting from the most narrow, ANI is basically quote unquote like weak AI. It's already in our day-to-day use. Usually this is limited to singular tasks. Think of, for example, playing chess on an iPhone app. At the other end of that, there is some sort of machine that's basically taking into consideration what are the moves you're making and then combating those with its own move. So artificial narrow intelligence already exists. The limitation to it is it's limited to one singular task or one singular scope. Again, think of many of the apps that you leverage. AGI, artificial general intelligence, is really more of a hypothetical still. This is like if you have seen the movie I, Robot, where a machine would be capable of understanding the world just like a human and can carry out similar tasks. Now, the reason it's called generalized is this still isn't, totally unrestricted. There's still restrictions within AGI. So usually think of one industry, one scope, or things of that nature. And then the last is ASI, which is totally theoretical and hypothetical. This is your quote unquote strongest AI if you want to classify it from that perspective. It's the level where intelligence exceeds the cognitive ability and performance of humans on all domains. So this would be realistically what you think of in that sci-fi space, that this is a robot or some sort of machine integration of the two that can basically exceed any sort of human cognitive function. Now, the types of AI also kind of correlate to this. It's very similar to biology. When you think of naming species and things like that, these two follow the same things, or it's almost like a family, and then you limit it to the types as well. So moving over to the right side of the screen, we have 4 different types: reactive machines, limited memory, theory of mind, and then self-awareness. And they go in increasing order of complexity if you want to think of it from that perspective. So from the reactive type, these machines basically have no memory and they're task specific. Again, they're reactive because they respond to an input. So if you want an example of this, think of Netflix. Anytime you log into Netflix, when it provides you recommendations, it's basically taking what you've currently seen, putting it through an algorithm, and spitting out like with like items. So this is taking a basic input, comparing a like item with it, and then that's what you get out as the output. It's typically reliable, works well. However, it requires to be fed appropriate information for it to work properly. Humans don't necessarily have the capability to digest such large amounts of information at once. So thus our day-to-day typically is not really known as sort of reactive, similar to how these machines are. I mean, think of it. If you were to take, there's 31 individuals currently on this call, and we were to put in everyone's movie inputs, show inputs, things of that nature, and you would be responsible for analyzing that and then spitting out sort of, okay, you would like this sort of similar movie or show. Difficult to do because of the amount of data. That's why it's limited in scope and more so reactive. Type 2 is what are called limited memory machines. So this algorithm starts to mimic our brain's neurons when working together. And this is going to be a common theme. Most AI framework is built very similarly to how the human brain works. So if you like neurology and thinking of neuronal pathways, you'll really like the discussion on the framework. So essentially, this builds layers of information. So each neuron, if you think of each neuron being responsible for each sort of muscle action or reaction or things like that, and multiple neurons build up to create layers and a network, that's the concept here. So this machine or this sort of AI algorithm basically takes information and consistently continues to build a network upon the previous existing information. To Richard's example in the chat, he mentioned Tesla. This is exactly what self-driving cars do. The more the car practices in theory, the more it will recognize differences in humans. For example, if you have, a child versus an adult, 2 different sizes, the more it practices with the difference between the two, the more it'll be able to realize and properly recognize those sort of inputs. Now, the last 2 I'm going to kind of group together: theory of mind and self-awareness. Because the reality is the first 2 types exist. Reactive machines and limited memory, we've already seen in day-to-day practice. The last 2, they're theoretic, they don't necessarily exist yet. Theory of mind and self-awareness are basically the ability to build multiple complex neuronal networks. So think of multiple layers on multiple sort of scales and spectrum. So not only understanding, for example, the Tesla model, where it's going to take in, the difference between a human and a tree, for example, but also in the reactive point, it's also going to be able to understand preferences and inputs and be able to put logic with that together. So self-awareness, the ability to understand how the world works and also understand itself respectively. Moving on from the actual designation, how does it all actually work? What does the framework actually look like? Well, artificial intelligence, or AI, we'll refer to it that way throughout the rest of the presentation, was a term actually first discussed and coined by Professor John McCarthy from Stanford in 1955. If you're interested in learning more about AI, I highly recommend looking up some of his papers. AI itself is defined as the science and engineering of making artificial intelligence machines. Although there are more than just two pathways to AI, the two most common themed pathways tend to be logic, so the left-hand base of that tree diagram that we have on the slide, and then the rules-based, or the right-hand side of the diagram that we have. Regardless of which pathway is taken in designing AI, the reality is both require the central basis of putting in inputs or data, conducting manipulation or analysis, and then sending out an output. So what you see on the left-hand side of the screen, two main pathways, and we'll go through them, the logic-based and the machine learning. But the right-hand side is sort of the premise for any sort of AI modeling that you do. Essentially, you'll need to figure out what data you're going to leverage that's going to be used for learning or training the actual model itself. You have to prepare and manipulate that data. The reality is most data is quote unquote dirty. You have to clean it up depending on what input specifically you want. You train the model with a few examples, and then you consistently improve the model. That's the part that most people tend to forget, especially from the machine learning aspect, is it's a continual improvement or continual building on what you've already done. So looking at logic and rules-based approaches, this is probably what most of you are familiar with if you've ever worked in some sort of epic or some sort of logic-based informatics role. While differences do exist between true logic and rules-based system, for the purposes of this overview, we'll kind of be referring to them synonymously. The basis of logic and rules-based system is like utilizing deductive reasoning. So if this, then this would happen. So for example, if I were to touch a hot stove, a natural reaction would be I'd probably want to pull my fingers away right away and maybe scream. So ultimately, you're given an inputs or data, and you run that input through a series of quote unquote rules or questions or cases, if you will, that help determine the final result of a solution. So in order to build a rules-based system, a developer first creates a list of rules and facts for the system to follow. An inference system then measures the information given against these rules. In this case, an inference engine measures the inputs against the rules. Usually it's done through, again, if-then statements. Think of if you've ever used Excel, for example, with if-then statements. The logic is very similar. The system follows the rules and repeats the process for every single input, and that's how your results sort of come out. Now, the general rule of thumb here is when classifying data and utilizing rules or logic is to start broad and then narrow down. Otherwise, if you start too narrow, you can contradict the other rules downstream. So again, the main concept, the main takeaway when you're building a logic and rules-based approach is you start broad and you almost funnel down to the final result that you want. So moving to the right hand of that diagram, machine learning. And the next few slides are probably where it starts to get a little more complex. Most people tend to have an understanding, especially if you've ever leveraged really critical thinking, deductive reasoning, how a rules or logic-based system works. Machine learning is sort of a cycle, if you will. And you can see that on the slide here, where it's sort of continuously, you'll see the arrows tend to follow each other and move in the same sort of cycle. So machine learning is the part of AI studying how computer systems can improve their perception, knowledge, thinking, or actions based on experience or data. Those are usually the main outputs that are put out. While the graphic you're seeing on the screen is a very simplistic representation of machine learning, the main concept I want to point your attention to is the need for constant reinforcement and enhancement for a machine learning model to be effective. It's very similar to how humans learn, right? I mean, think about it, from the time that we were in kindergarten all the way through, finishing high school and then secondary education or whatever, you're continuously building on skill sets. Think of mathematics, right? First, you start off with simple 2 plus 2, all the way up to advanced algorithm, calculus, things of that nature. Same sort of concept, that you keep building that main foundation and it consistently build on that. In order for machine learning to be successful, the first item to understand goes back to the old saying that 99% of your time should be spent understanding the problem, 1% actually solving the issue. Machine learning starts with a simple question or ask that you are trying to solve for. So similar to the rules and logic-based approach we discussed, the next step is to understand and identify the data needs and then actually collecting, cleaning, and preparing the data for model training. Now, if you're looking at the graphic, we're on the left side where it says sort of data prep. So kind of the purplish salmon colored slides there. And similar to working in an Excel file, data preparation requires making sure your data is holistic and complete, replacing the missing data or gaps as well, deduplicating any redundant information, and then spitting the data out into a training, testing, and validation sets. And that's really a key important component of machine learning. Most people think that machine learning is simply, okay, I'm going to take the same set of data, put it into this model, and then it'll replicate it right away. The point of validation comes into here, where you see on the slide where it says like human adjust the model, data points that don't fit the model well. The reality is you want to start with such a large amount of data that you can break it down into your test data, so what you're going to actually test the validation, your training data, so what you're following along the machine learning, that point where it says the data point doesn't fit the model well, you make those adjustments consistently with that training data, and then you test it with data that it's never seen before. So again, that first step when you get to that point is answering that question of what are you actually solving for and splitting up the data appropriately. Jumping into the data segmentation discussion. So you'll see two pathways on the screen here. The pathway on the left, the purple, resembles a training pipeline in which your set of data is presented in original state, clean, and then vectorized. And the main principle of machine learning relies on algorithms identifying patterns within data. This could be sound, pictures, text. I mean, think of Google now. You could take a picture of a flower, right? Put it through the Google system, and it'll tell you, okay, this flower is most likely XYZ species just based off the picture. There's a lot of things coming out now that are more sound and more so combining the two. Think of, for example, anytime you ask Siri, what's the song playing, right? That's exactly a similar sort of algorithm that it's using. It's taking a snippet and it's basically vectorizing, or looking at what's like to like enough and hitting a threshold that says, okay, I have X amount of confidence in stating that this is the right output based on it matching up X%. So in order for the recognition to occur, you have to conduct vectorization. And again, basically, this is extraction of distinct features out of a text or data for the model to be able to train on and convert those into numerical vectors. So vectorization can rely on multiple coding languages, but essentially you are correlating numerical value with an input that's specific to that one feature that you're looking that makes it different, or for the model to recognize the difference. Now, the right side of this data set, or sort of the aquamarine-ish color, if you will, the light blue boxes, are new, never before seen data. And you'll notice the steps missing on the right side are the testing set and validation. Instead, this time we leverage inference again, or the compile time process of reconstructing missing types of information in a program based on the usage of its variable to produce an output. So again, the importance of when you're looking at data and you're looking at training and things like that, you have your training set, you have your testing set, and then you have your validation, and then it goes into a live production state. Diving deeper into the algorithms. Again, I said AI is very complex, right? This is a high level overview, and we're sort of starting at the broad level and narrowing down into some of the algorithms and things like that. By the end of this presentation, I don't expect any of you to have a truly, deep understanding or knowledge to be able to build out these algorithms, but instead going through the differences in learning styles for machine learning, because this directly kind of correlates to the precision and accuracy of an output, which when you think of pharmacy practice and you think of what's at stake, we are dealing with patients' lives for the most part, you want to make sure that you have some sort of precision and accuracy. So on the top of the chart, you'll see that machine learning is divided into supervised learning, unsupervised learning, and then reinforcement learning. So supervised learning is an approach defined by labeled data sets. So these data sets are designed to supervise or train algorithms into classifying data or predicting outcomes correctly. So basically, this has a massive human need and effort up front. An example of supervised learning would be to take photos with dogs, provide information on which dog is which, and then train the machine to recognize more photos with the respective dogs. So supervised learning utilizes basically classification and regression. In a clinical setting, think of some of the clinical decision support tools, right? Where, for example, warfarin will probably be classified with the lab result of INR. Tacrolimus might be classified with a lab result of an FK506 lab, right? So the next thing to understand is classification underneath supervised learning. And classification is basically the machine is trained to classify something into a class. So for example, whether it's a patient has a disease. Regression, on the other hand, right next to it in the kind of aquamarine light blue color under supervised learning, is when the machine is trained to predict some sort of value like price, weight, or height. For example, think of financial modeling, right? Predicting price, property, or stock pricing based on historical results. Same thing can be used for trending in a clinical setting, right? So that's supervised learning. Again, the main takeaway with supervised learning is it requires a lot of upfront human input to build it out correctly. Unsupervised learning, or the very middle, those sort of green, light greenish, uses algorithms to analyze and cluster unlabeled data sets. So unsupervised learning leverages hidden patterns within data without the need for human intervention. So in the examples I gave with the photos with the dogs, if we were to use an example of unsupervised learning, in this example, this would be having a bunch of photos with 6 different dogs, but no information on which dog is which. The goal here would be to divide the photos into 6 piles, each with the photos of one individual dog. So even if there's more than one group of dogs in one photo, if it's divided into 6 separate piles, for example, let's say you have a husky in your pile 1, it'll try to cluster all the pictures with huskies into pile 1. Pile 2 might be another species, so on and so forth. So it's all about leveraging clustering or association primarily. Unsupervised learning, although more efficient because it doesn't have as much human input in the beginning, when tested through a lot of medical modeling or medical algorithms, doesn't tend to prove to be as specific or concise, because a lot of times in medicine you have to take multiple considerations. For example, think of infectious diseases, where you're not only looking at maybe the temperature of the patient, you're looking at white blood cell, you're looking at microbiology cultures, speciation of sort of culture data, things like that. It's more difficult unless you build out those input ahead of time. Again, clustering in this, similar to how we broke it down into classification and regression, clustering is when a problem is where you want to discover the inheriting groupings in the data. So for example, grouping customers by purchasing behavior, versus there's also another type under unsupervised, that's association, which is when you want to discover rules that describe larger portions of the data. So for example, people that buy a phone often tend to buy a screen protector. So unsupervised learning is leveraged a lot in social media, in ad marketing. If you've ever wondered, why am I getting this ad on your Facebook or Instagram or whatever it might be due to association or clustering, where maybe you looked up one thing, like in the example of someone buying a phone, it's automatically assuming that you want a screen protector. And then on the right-hand side, you'll see reinforcement learning. So reinforcement learning is a technique that trains software to make decisions to achieve optimal results. This usually mimics trial and error learning processes, like those that humans use to achieve their goals. So as an example of this would be autonomous driving cars, where the dynamic environment allows it to constantly trial and error what works and what doesn't. The best use case, and probably the most documented use case of this, is the differences between humans and different sort of other vehicles or obstacles on the road. The trial and error is basically, can the Tesla or the automatic car identify those differences? The more it practices, the more it'll build out that, for example, a truck is an obstacle, but a truck has multiple brands, right? There's a Ford, there's a Chevy, there's a Dodge. They might be different sizes. And the more it sees examples, the more trials itself through that, the better it'll get. Towards the beginning of this presentation, you heard me mention that this deep learning and sort of machine learning and AI, they're structured based very similar off of the neurologic framework that's in humans. So as processors have become more powerful and algorithms have become more efficient, a new wave of machine learning called deep learning is starting to take shape. And this is what you're starting to see more and more of in the news. So although there is no exact definition to what deep learning is, it's still classified under artificial intelligence. The main difference is, while artificial intelligence leverages algorithms developed for specific tasks, deep learning uses matrices of data that are layered, similar to like the brain. Each layer utilizes outputs from the previous layer as an input. So deep learning is meant to represent more of the human brain and natural functioning. For example, deep learning can not only tell an object is a car, but it can tell you where that car will be dependent on speed. Think of your car sort of tracking, or if you have one of those cars that has the automatic cruise control and keep up with the cars in front of you, it's using that sort of learning to not only know that, hey, there's an obstacle in front of me, but I can also track based on how quickly it's passing other inputs, like maybe a tree on the side of the road, or maybe the amount of markers in the road, run some math and learn that, oh, I need to stay X amount of distance behind this car in order to not run into it. So the core behind deep learning and truly all of AI is connections, data labeling, categorization, pattern recognition, and then mathematical statistics. So all of this together makes up a neuronal network, similar to like the human mind. In networks, multiple inputs can represent multiple outputs, and the missing piece is really the hidden layers of all of the if-stens that correlate to the correct output. So what do I mean by that? For example, a car can go and a car can stop, right? That's one input. The car is going, two different outputs. It can continue going or it can stop. A hidden layer, maybe the red light represents stop while the green light represents go. So now you have one layer, a car is going, two different outputs, right? The output is either it continues going or it stops going. The neuronal layer above it might actually be the red light, or a stoplight in general correlates to a car's action. Red means stop, green means go, yellow means caution. So if a car is approaching a green light, the neuronal network may trigger the input to be the car, output's going to be go or stop, and then run them at lightning speed against all of their outputs and realize that green usually correlates with go. And if those two match, the output would be that the car continues going. It might trigger another output or another layer if it's looking at speed in correlation to distance, where the final output after all the layers may be knowing exactly where the car will stop and analyzing the data over a mile stretch. So as you can see, it's very complex with deep learning, because all of those little, if you look at that center where it says feature extraction and classification, you have all of those little pathways. That's basically the problem that deep learning is trying to solve for, right? Which of those pathways best correlates the path forward? Of course, like any sort of prediction modeling, forecasting, anything that you do, whether it's financial or any industry, there's always going to be bias, and accuracy has to be taken into consideration, especially when we start talking about some of the pharmacy specific applications. So when we discuss this in terms of AI, we leverage the terminology of bias and variance. So bias refers to situations where the model makes erroneous assumptions. Variance, on the other hand, refers to the specificity the system has to the trained data and its ability to properly classify new data correctly. So ideally, you would want a situation where you have low bias and low variance, or in other words, high precision and high accuracy. So as you can see from the many models previously discussed, different types of learning, whether supervised, unsupervised, etc., there are many opportunities to accidentally build in biases and incorrect assumptions or classifications. Before we dive any deeper, we're going to do a quick application check. In this application check, we're going to do a group case looking at dispensing logic. So again, this is using logic and rules-based sort of framework. So the scenario is you are utilizing logic and rules-based approach to determine the dispensing location of a tablet of 5 milligrams of warfarin. So the ask is to place the steps in the correct order from the dispensing machine to dispense the correct drug and dose, again, using logic and rules-based approach. Choice number one, and again, the goal is to rank these, is if an order contains quote-unquote warfarin, then dispense from Omnicell or Central Pharmacy. Choice number two, if order contains 2 milligrams, then dispense from Central Pharmacy. Choice number three, if order contains tablet, then dispense from Omnicell, Central Pharmacy, and anesthesia cart locations. And then choice number four, if order contains 1 milligram, 5 milligram, or 10 milligram, then dispense from Omnicell. All right, so let's actually talk through the answer choices here. In this situation, again, the goal is to start, if we think of sort of like a funnel, we want to start with the least limiting factor, right? Or as broad as we want, and then sort of narrow down. So for that reason, We leverage the dosage form first because it captures the largest classification. So basically utilizing if an order contains tablet, then dispense from Omnicell, central pharmacy, and anesthesia cart locations. You'll notice in the choices below, anesthesia carts are never mentioned, right? And warfarin is more specific than tablet itself. So start with tablet, then we go by drug next. We want to limit our pool based on the specific drug name. So if we were to start with the dose first, then we could potentially exclude drug name since it's more specific or narrow. So if we were to start with 1 milligram, 5, or 10 before getting to warfarin, it might exclude that accidentally. And then lastly, we pair with our most specific feature, the dose itself. So now in this case, you'll notice that the 2 milligrams I placed last or in red. The reason it's in red, it doesn't mean it's the correct answer. The reality is, for this example where we're looking to narrow to 5 milligrams, the 2 milligrams is erroneous information. You don't necessarily need it in order to get the dispense logic correctly for the 1, 5, or 10 milligrams. So that's why I placed it at the end. The reality is you could place these two equal to each other, right? Because they're not going to interact with one another. So you could place a statement saying, okay, if it contains 2 milligrams, then dispense from central pharmacy. Or if it contains 1 milligram, 5 milligram, or 10 milligrams, dispense from Omnicell, because 2 milligrams or the 1, 5, or 10 don't switch their dispensing locations and vice versa. So the order, again, we start broad tablet, drug name, then doses, and then I threw one erroneous in there that doesn't necessarily correlate. What does it actually mean from a workplace implications and opportunities? Now we're going to start getting more into the pharmacy specific aspects. Before we do that, I actually want to do a think, pair, share. In an in-person setting, I'd say turn to the person next to you and chat about this. Here, we're going to use the chat feature. What are some applications you have seen of AI in healthcare or proposed uses of AI in healthcare? And I'll read the chat as I get answers. So Epic dispense logic. I've seen reading x-rays, so more on the diagnostic end. Prior authorization. Okay, so automation of tasks. Diversion analytics, absolutely. Allergy flags. When ordering medications, Epic, our medical record system will suggest a programmed dose. Yes. So predictive dosing, dose warnings. These are all great examples. HR applications, yes, many companies are now using AI to screen for certain words or things on a resume or CV that they're looking for. That's correct. Inventory management. This is a growing area within supply chain using AI for predictability. All great examples. Predictive vancomycin dosing, again, perfect. The reality is, and the question that I get all the time working in analytics, is AI going to take over my job? Is AI really going to be able to do what we do in healthcare and things like that? So what's interesting, I thought I'd include some statistics and put some numbers to it. I'm a numbers guy. So at the end of 2022, OpenAI launched ChatGPT. I'm sure we've all heard of it at this point. It's been in a lot of news, a lot of different other forums. And since then, almost every industry has taken at least a look at adopting some sort of AI interface or capability. So what does that actually mean from a numbers perspective, right? In the current state, AI has over 100 million users specific to ChatGPT and over 200 plugins available. And research from 2023 shows no signs of slowing this down. So in collaboration with the University of Pennsylvania, OpenAI conducted a survey of top companies, and it's predicting that 80% of all US workers could have 10% of their work tasks affected by GPTs, while another 19% of US workers may see at least 50% of their tasks impacted. So the reality is AI is here to stay, whether we want it to or not. The reality is AI has been here for a while. Again, going back to the example of even using an app on your phone to play chess against a computer. So what does it actually look like from a breakdown perspective? So I got this off OpenAI's direct website for ChatGPT. And while this list isn't even scratching the surface of capabilities, you'll notice a common trend here. As you read through these tasks, you may think that a lot of these impact you or your day-to-day. The reality is the biggest use case of GPTs specifically has been to supplement and augment day-to-day tasks and allow those tasks that truly require human input to be the focus of the day-to-day. So when I get the question of will ChatGPTs replace the workforce, the reality is it could replace some of the workforce, but not completely all of it. Think of the example of how much easier it is to communicate now versus years ago prior to email. Think of research at your fingertips now using an iPhone even versus having to go to a library to do a research paper. The reality is AI, like any technology, is no different. The only difference is, by definition, technology is the application of conceptual knowledge for achieving practical goals in a reproducible way. This is not necessarily the definition of AI. So, where do I see AI falling into place, at least for the next 5 or so years, maybe even a little longer? Is more so a supplement to the day to day. You can see some tasks on here: email writing, email composition, an executive perspective, using it for scheduling, things like that. Research, compilations of content, things like that. Basically being second set of eyes, right? If you already have something, you could program a GPT to say, for example, you're a marketing expert, go through and social mediafy this, statement that I want to put on LinkedIn or whatever the case may be. Those are all supplements. They're not necessarily the core day-to-day of what someone's doing. Let's look at some actual practical use cases of this in pharmacy. Where have we seen this? First leveraged as computer software in the 1970s, clinical decision support systems have been around for a while. Think back to any sort of, quote unquote, smart guide or dosing guide. The reality is that this is the perfect area for integration within pharmacy and AI. Clinical support and decisions usually rely on inputs, data such as lab results, imaging, things of that nature, in order to create an output, treatment or dosing recommendation, if utilizing weight and height to help determine dosing weight or creatinine clearance, for example. The core basis of AI is leveraging data points and inputs to create this output. So one of the best cases showcasing the impact of a robust clinical decision support system is one that's actually augmented with AI. And this was actually out of Good Shepherd in East Texas. Keep in mind, this system was built on a rudimentary logic-based AI system, not a true machine learning aspect, which is what some clinical decision support is starting to go to. But Good Shepherd was able to showcase actually going from 1,986 interventions monthly from their pharmacy departments all the way to a whopping 4,065 clinical interventions guided by a clinical decision support model based off of a Logix AI system. That's over 105% increase in productivity month over month. This was able to correlate to a cost savings just shy of $3 million, or a 96% on return per year for them for integrating this technology. So how does it look like in actual practice, right? It's one thing to say, great, the numbers look good and they were able to get this massive return and all this sort of stuff. What's it actually look like? So you'll notice on the slide that the title alludes to one of the biggest concerns in AI, which is the concern to replace human intervention, or basically, will AI replace my job? I would say the better question is, how accurate or precise can AI be in comparison to human intervention or as a supplement to? What AI can do is provide more accurate results more efficiently. So think of it this way. Imagine you want to invest in the stock market and are between two stocks. In scenario one, you have to compile and comb through multiple data cases, past history, past data, etc. In scenario two, you have a summary of the average historical results and can leverage those to create a prediction on where the stock will end up. So I'm not going to be looking at basically month to month. I might be looking at, okay, this year compared to this year, right? Which scenario seems easier? Probably scenario number two, right? Where it's an aggregated or concise compiled review. And in either scenario, the final decision is still based on the human to make the input, right? So a great example of this, leveraging AI and machine learning to predict outcomes from medication dosing. So there was a study looking at tacrolimus dosing, and machine learning was placed against traditional monitoring and AUC calculations. The machine learning looked at 4,997 tacrolimus doses at twice daily dosing and 1,452 doses at daily dosing. Monitoring was done pre-dose, 1 hour, and then 3 hours after dosing. And in this model, 75% of the patient populations were leveraged for training, and then 25% were leveraged for validation. So again, like we discussed, where you have to break up your data points, out of all of this data, 75% went into training, and then 25% was a validation. So of this, And running this through compared to humans that at the same sort of monitoring had the same data points, machine learning actually outperformed what actually happened and where the prediction was going to be for the next level and what the next dose should be from hypothesized across the board within 2 standard deviations of error. That's pretty impressive to me. But think of how much data had to go input into that and how much of that build out had to happen in order to get it to that state. While it sounds great in theory, right? We just had an example where we saw that tacrolimus dosing was actually more accurate to what actually happened looking back retrospectively from a hypothesized perspective. I can't stress the importance of the cost and complexity of building out a proper neural network needed for accurate clinical precision. So as you can see here, the health system is set up as an ideal use case for artificial intelligence because almost every aspect or every phase of care or things like that is associated with some sort of data highway that could require continuous learning. Think about it. Every time you get a lab, that's a data point. Every time, for example, someone brought up inventory management, an item is purchased or moved, whether in stock or out of stock, those are multiple data points, right? Every time you look at the reaction from a medication and get continuous labs, again, multiple data points building up. The problem is, though, with such large data, there comes a massive cost of actually manipulating the data and cleaning it up appropriately. So let's look at it from the industry perspective. Hit discovery. This is a practice in drug discovery, and this is an area where I do think the funding may actually be worth it, and the technology may be there to be able to get us to a point to discover medications more efficiently. So hit discovery is a practice in drug discovery and other sciences in which disease state modeling is created and validated against public databases. So think of like PubMed, PubChem, things like that, or proprietary information, chemical libraries. The purpose is to identify a quote unquote hit or a chemical structure or compound that is of interest from a clinical perspective that's similar to something that we already know works or has been theorized to work. The goal is to see if this hit can assist in other clinical disease states or has another purpose that's unknown. So it's basically running through multiple simulations. By targeting certain chemical structures in simulation modeling, you can actually detect the potential impact in other scenarios. So in the example above, Excentia and Sumitomo co-developed a molecule called DSP-1181, a drug targeting obsessive compulsive disorder. The average industry time for preclinical testing is usually 4 to 6 years. So think of all that cost associated to bring this to market. Where did it actually work and what actually happened? It brought it down from machine learning and AI to a streamlined timeline of 12 months of testing. So you can imagine you basically shaved off a minimum of 3 years up to 5 years in testing to be able to bring this molecule to market. So the cost benefit perspective within industry tends to be where most of the use case is going. Let's look at an operational use case. So another promising aspect of AI-enabled pharmacy technologies is looking at predictability within actual inventory shortages and inventory modeling. So the above is an actual example that my team helped co-lead, looking at the current demand for BCG through the End Drug Shortages Alliance. And what we were able to find is that actually only 69% of the actual demand was being met. The key here is we didn't necessarily use AI to create this model, but this is an example where AI could have helped us because this analysis took a while to complete. There's a lot of data you have to gather from what's actually used to what's projected, compare that to how many patients go untreated, and then figure out that delta difference basically. Now imagine an AI model if we were to feed these data inputs and it could spit out, okay, I'm projecting that your utilization based on the past before this went on shortage, assuming X amount percentage increase, you're short this sort of percentage instead. So again, while I don't have the time exactly of the difference between what an AI model could have projected for this versus the time it took us, I'm fairly confident in saying that it probably could have expedited our results massively. So now let's look through some application exercises. And the most common feature that most people are familiar with now are chatbots. So let's use this to help us counsel a patient. In this exercise, I'm going to ask you to basically help me develop a counseling plan for warfarin therapy. So you'll see on the screen here, This is an exact screenshot from what ChatGPT looks like. The scenario is we're asking for counseling help on a patient on warfarin therapy. And the goal is here that you have to look at how you're actually asking these questions because that'll dictate the response. So, what if I was simply to ask ChatGPT, drug information warfarin? We would get almost a monograph like response. In this situation, the information is fairly accurate, yes, but it's done so at a really high level. And this is no different than what you can look up online from the actual monograph. So, in terms of actually counseling your patient, you could theoretically read off indications, warfarin commonly prescribed for XYZ, but it doesn't really have the answer that you're looking for, right? Again, we started off with really basic drug information warfarin. So what if we gave us some context to make ChatGPT and set the premise or the case or the limitations, if you will, of what we wanted to do? So in this instant, we ask it, you are a clinical pharmacist counseling a patient on warfarin. Please design the dialogue. So while the information is primarily there, it comes out in a weird format, right? It says, patient, hi, I've been prescribed warfarin, but I'm a bit nervous about taking it. Can you tell me more about it? Pharmacist goes on, of course, I understand your concerns, etc. It's literally dictating a full dialogue between patient and pharmacist. The problem here is that might not necessarily apply to actuality of what we want those statements to look like. So instead, we refine it and say, okay, keeping the contents, you're a clinical pharmacist, provide me counseling points with warfarin. This time, we don't necessarily give as much background, right? But we're strictly focusing on the counseling points. Now you'll see here, it starts getting a little more specific. It starts giving you dosage administration down to bleed risk, etc., things like that, with bullet pointed information of what to talk about. And now the goal is you have to augment this with your own clinical expertise and basically figure out which of these bullet points that you're going to talk about in actual dialogue. So what's the difference? Why do we go through that exercise? You'll notice in the top box, the drug information warfarin versus the bottom box where it says provide me counseling points for warfarin. Even though most of the information is similar, there are differences. For example, we asked about drug information warfarin and provide me counseling points. They're close, but if you look at the verbiage, they are a little different. The drug information is more so monograph format. The counseling points actually talk about, hey, if you are on medication or supplementations, you should talk to your pharmacist or doctor because there are interactions, etc., things like that. The exercise we just went through and how you optimize ChatGPT is called prompt engineering. It's a very similar concept to logic and rules-based approach. Essentially, you're setting up the scenario, roles, goals, and also leveraging constraints. So in general, you want to provide a succinct prompt without being too limiting, while additionally, it helps you provide context through roles and then leverage positive prompting or inclusions that you want in there. So for example, you're a clinical pharmacist with 10 years of experience. Your goal is to provide a summary of P450 interactions with warfarin versus negative prompting, which is where you want an exclusion. So in the example above, you would say exclude those interactions with warfarin that decrease warfarin concentrations. So you have to think through again, what are you trying to solve for? And what if then statements would you want in there to get the correct answer? And that's how you best leverage ChatGPTs. The last question is, how applicable is this, right? We all know pharmacy has red tape. We all know medicine has red tape. They're highly regulated professions. According to IBM in 2023, 35% of organizations are now admitting to leveraging some sort of AI platform and capability, and that number is exponentially increasing. While if you look at and compare that to the National Conference of State Legislators compiled data in the 2023 legislative session, and at least 25 states, including Puerto Rico and the District of Columbia, introduced some sort of artificial intelligence bill, and then 18 states actually adopted resolutions or actually enacted the legislation. So a majority of these themes centered around the definition of what a human is, or an entity, or a person, to not include artificial intelligence and protect against cybersecurity attacks and protection of privacy while also looking at ownership rights of data. Now, in combing through some of these resources, it's evident that most of the legislation is not actually healthcare or any industry specific, but more so generalized. And if we take the general premise that use the law that's more specific is the one that kind of supersedes the other, most healthcare laws actually are more specific than what some of these artificial intelligence bills and legislations are actually alluding to. So what does that mean in actual practice? The actual practice and my recommendation would be to be careful with leveraging AI technologies in your day-to-day practice. One of the biggest problems facing healthcare AI development is the fact that all machine learning and AI require extensive data sets and continuous training in order to develop specificity and accuracy and develop those connected neuronal networks that we talked about. However, healthcare being one of the most regulated industries, information isn't readily available because it's protected. Think of PHI, think of HIPAA, think of even your local policies at your institution. And this is where my big caution comes in. I would be very cautious in placing patient-specific information or organizational information in any sort of chatbot that isn't vetted by your IT department, because the reality is the liability is there. Another aspect that's come up is most legislators are pretty much on edge with who's actually liable if something does happen. And this question of liability actually came up from a Long Island University College of Pharmacy did a study from January 22 to April of 23rd, asking a chatbot about 45 unique clinical questions. Of this, the accuracy of the chatbot was 26%, as deemed by two external validation groups of medical professionals and clinical pharmacists. It was noted in one example that this was dependent on the information available at the time. So for example, one question looked at the correlation between Paxlovid and verapamil for cause of hypertension when taken together. The information the chatbot had at the time showed no interaction. It wasn't until Paxlovid wasn't approved until December of 21, and that was a few months after the prior data set cutoff for what this chatbot was fed. So they reran it with the new information, and the chatbot was able to determine that there is an interaction, but wasn't able to give specificity on whether it was hypotension or not. So you can see now how the information you're feeding is also an issue. Many companies, and what the current state is they're opening for a closed source data loop. If you think of ChatGPT online, it uses an open source data. It's basically data scrubbing across the board and pretty much pulling in multiple data sets. Most companies, most institutions have implemented their own version of a ChatGPT, but they've blocked off that data at some point. That's another cautionary point. So if you're using this, for example, for inventory management, or even clinical, if something new were to come out and you're not sure at what point your data was cut off and whether it includes it or not, that might indirectly impact the output there, because it essentially freezes that data at a certain time point. So the ultimate recommendation, looking at legislation, looking at also what current companies are doing, where they're really recommending against putting things into a public domain or like ChatGPT itself and using their internal. The limitations are that you're using only one subsegment of data. It's not a continuously evolving thing unless your IT or whoever built out the GPT specific to your organization is providing you with what those updates are. I would be careful with leveraging that information. I would be also careful with PHI and things like that, because as we've seen with cyber attacks and things like that, most of these platforms being open source, people are pulling a lot of data. You can even look at competing companies, employees that have accidentally put in data into ChatGPT. You can see some of even like competitors for different companies, their proprietary information on there. So the caution would be to be careful with putting any information on there. Use your own discretion, but also don't forget that your cognitive ability and the ability to take in all the information may have a holistic, better view of what's actually happening versus the limited data set that your organization-specific GPT might have. So with that, I know that was a power hour of going through AI, framework, all that sort of stuff. And I'll open up the floor to any questions now. So one question I have in the chat, have you seen AI in healthcare used to increase sales? Are you talking in terms of from an industry perspective, or like actual like salespeople leveraging information, sales and results that would drive usage or test results? Okay. So AI specifically in healthcare, I haven't seen anything that would necessarily drive sales. I will say AI in supply chain, which I think is where healthcare supply chain is also starting to catch up. There are some companies, if you want a great company, Walmart is actually a great use case of they are not in the retail industry. They are in logistics and data. And if you look at the framework they've built out with AI and the amount of purchasing data they have, a lot of their systems from their POS, so their point of sale system, all the way to their ordering and inventory is 90+% automated and fairly accurate. There's a reason why they're rarely out of stock on things when you go into their stores outside of massive, unforeseen events or things like that. So I think healthcare is starting to catch up in that aspect. The problem again is when you think of healthcare and you think of drug supply chain or even general medical surge supply chain, there's a lot of data gaps and a lot of different company competitors. And in order for AI to truly be predictable or help you within that inventory management or drive sales or things like that, you would have to have information from your competitors as well to look at the marketplace as a whole. A lot of that from the current state that I'm aware of, at least, there's a lot of gaps in trying to get that information outside of your respective organization. So I hope that answers your question. Thank you all for having me today, and thank you for joining me. If you do have any questions, please don't hesitate to reach out. My email is on the screen there.